we still have one more topic that I kind of need to touch on, and then we just need a day to probably tie all these topics kind of back together, and then a day for review. So maybe end of next week or beginning of the week after. Because there's a lot of things here that we had to kind of get through. Okay. So we're still talking about solving. And we've talked about factoring as our lone solving technique to this point. Today we're going to add two more solving techniques to our arsenal. So the reason we need more techniques is because, well, what's the catch with factoring? Is not every polynomial is factorable. So we can't use solving to say solve for something like this. Or can't use factoring to solve something like this. X squared plus 3x plus 5. What's wrong with that? There's not two integers that multiply to give me 5 and then add to give me 3, right? So we're going to have to cook up some other methods to use for situations such as that. Okay. Our next method is we're going to do or talk about is, say, solving directly. Sure. Let's do that, do that, do that. Okay. So, if I look here, the left-hand side is clearly quadratic, right? Because I have a x squared. Notice, though, what's missing on the left-hand side is I have no plain x's. Do you guys see that? So I have no plain x's, I have only x squareds. This is the situation where I want to be using a direct solving technique, is when I have only one kind of x. I don't have x's and x squareds. Is everybody okay with that idea? So when we say solving directly, basically what we're going to do is we're just going to use the order of operations in reverse. So when you're simplifying something, we go parentheses, exponents, multiplication, division, addition, subtraction. When we're solving something, we undo those operations in the reverse order: subtraction, addition, division, multiplication, exponents, parentheses. So if I take a look at 4x squared minus 9, the first thing I'd want to do would be to it's not a trick question. Just add 9. So we've canceled off the addition and subtraction. So the next thing I should do is divide by 4. So we've undone any multiplication divisions now, right? What should I do next? Square root both sides. Now this is an important question. When I square root both sides, what do I have to remember? So while I don't mind any of those answers, it's not really what I'm looking for right here. So when I square root both sides of an equation, something special happens, as opposed to just taking the square root of a number. When I square root both sides of an equation, I create a plus or minus. Now I would say that at least 2/3 of students consistently forget their plus or minuses in this course. So I'm going to take a moment here and just reiterate that anytime you take the square root to both sides of an equation, you generate a plus or minus. Please don't forget this. It's an easy thing to forget, but it's a really important thing because you're omitting several answers in some cases by doing that. Now, to square root a fraction like 9/4, Jack said we can square root the top and square root the bottom separately, which is correct. So the square root of 9 is 3, and the square root of 4 is 2. So we can say this. What happens if we have something like this? What should I do first? Add 8. I like that. Okay, and then what? Divide by 25. Good. And then square root both sides. What do I have to remember? Can I get everybody to say it? Thank you. And now to square root 8/25, I'm going to square root the 8, which is not a perfect square, and square root the 25, which is just 5. Now, we can do a little bit better than the square root of 8. So, if I do a prime factorization of 8, I get that 8 is equal to 2 times 2 times 2, right? So inside of there, I noticed that I had a perfect square, right? So if I want to talk about the square root of 8, I can think about it as the square root of 2 times the square root of 4, which is just regular 2. On this step, if you're doing this, if you're able to do those steps correctly on the test or whatever, I would count those as extra credits. So if you have square root of 8 and that's correct, that's fine, full credit. If you simplify the square root of 8 correctly, I would give extra credit for that slightly more reduced answer. Okay, so we're building towards something here. What if I have a problem like this? Can I solve directly with this kind of problem? Sure I can. If I look at this side, how many kinds of x's do we see? I see just one kind of x, right? I don't see both x's and x squareds. I just see one kind of x. Do you guys agree with that? So we can solve this directly, and as Jack has suggested, we can start by subtracting 10 from both sides. Then what should we do? Divide by negative 5. We definitely don't want to FOIL this out or multiply this out or expand this out. The reason being, if we do that, we're going to end up with more than one kind of x and no longer be able to solve this directly. Everybody okay to getting to here? What can I do now? I got to get rid of that exponent on the parentheses, right? What should I do now? Oh, you cannot ever distribute an exponent. Well, if I do that, I'm going to create more than one kind of x, and I'm going to ruin being able to do the direct solving. It's easier than any of those things that you guys have suggested. Just take the square root of both sides. When I take the square root of both sides, what do I have to remember? There you go. Somebody's paying attention. And because I can't take the square root of 5, I'm just going to write it as the square root of 5. And because the square root of 5 contains no perfect square factors, I know I can't do anything to make that any simpler, so I can just leave that. Okay. Now what? Add 3. Now, can I add 3 to the square root of 5? Definitely not, because they're not like terms. So how do I write this? I just write 3 plus or minus the square root of 5. Don't want to end up with a negative answer. I'm not sure I understand. But you could certainly end up with a negative answer. Okay. That's definitely possible. Is everybody okay there? So notice, what kind of an answer do we have here? This is not an integer, right? Because of that square root of 5 in there. This is a problem that we could not have solved factoring, but we can solve directly, provided that our polynomial was in this kind of vertex form situation. Do we know how to take a polynomial and put it into vertex form? Yeah. Yes. How do we do that? It is in our notes somewhere. There's a name for that process. Does anyone remember the name for that process?
I actually remember this. It's like you did a thing with like the arrows going from each thing.
Yeah.
It's not expansion, is it?
It's not expanding.
I know I'm close to it. If anybody else is, I'm going to be kind of upset. Foiling? Wait, going from which one to which?
So we want to find out how to go from here in standard form to vertex form.
I had it here, but I don't have that one. Is it not foiling?
So foiling is to go from intercept form to standard form. Factoring goes from standard form to intercept form. Expanding went from vertex form to standard form. Dots was a factoring technique. It is a abbreviation, though. CTS. Marshall? Yes, that's what we're looking for. CTS, which stands for completing the square. Which, ugh. So, here's the observation, though. Hold on. You're right. You're right that process is not a lot of fun. So, here's what we're going to do. I make the observation that process for completing the square is the same every single time, right? The numbers might get junkier, but I do the same steps every single time, right? So if I take a general polynomial and I do the completing the square process on it, what I can create is a formula that allow me to shortcut around having to do completing the square every single time. That's what I want to do. So let's do that. Everybody agree that that sounds like a much better option than doing the completing the square process over and over and over again if we need to use this? Okay. So what we're going to do is we're going to take just a generic polynomial in standard form. We're going to do the completing the square process on it. To get a polynomial in vertex form where we can then solve directly. That's kind of our plan, what we're going to try to do right here. And then what we're going to end up with is a formula that allows us to shortcut around having to do the completing the square process every single time. Everybody okay with that idea? All right. So this process that we're about to do, will I ever ask you to repeat this process to show me how this happens? No, I will not. I'm going to be very honest. I would not ask you to repeat this. It's a rather complicated process. But I think it's important that we see where this formula is coming from and how you could go about generating a formula like this. Okay? So if you'd like to take notes on this, you're welcome to do so. If you want to sit and watch, that's fine. We'll tell you at the end when we get to the kind of the payoff what the big takeaway is and what you would certainly need to have. But getting to that result, would not expect you guys to be able to reproduce. Okay? All right. So first things first, I want to do completing the square on ax squared plus bx plus c. The first step in completing the square is make the leading coefficient 1. How am I going to make that leading coefficient 1? Divide both sides by a, right? That's going to give me, x squared plus b over ax plus c over a equals 0. The next step in our completing the square process is we wanted to move that constant term to the other side. So I'll just subtract both sides by c over a. The next step is that I'm going to add b over a divided by 2 squared to both sides. Now I know that this side factors because it's a perfect square. It factors in a very specific way. It's going to factor into something plus something squared. The first something comes from the first piece. The second something comes from the second piece. And now I'm just going to multiply out the things on the right-hand side. So b over 2 squared, I can do that by squaring the top. B squared is just b squared. And then squaring the bottom. 2a squared is 2a times 2a. So that's 4a squared. Everybody okay here? So far, so good? What I'm going to do now is I'm going to combine the like terms on the right-hand side. To combine the terms there, I need to have a common denominator. The common denominator between 4a squared and a is just going to be 4a squared. So I need to multiply c over a by 4a over 4a. That allow me to write that as a single fraction. And now to solve, I'm just going to square root both sides. So when I do that, I have to remember what? Plus or minus. And when I square root a fraction, I'm going to square root the top and square root the bottom. Now I can't simplify b squared minus 4ac because of the subtraction symbol. But I can square root 4a squared in the denominator. So the square root of 4 is 2, and the square root of a squared is just a. And my last step then will be to subtract b over 2a from both sides. Notice there that these two things have a common denominator, so I can just write them as a single big fraction, which is what I'm going to do. And what I'm left with, hopefully, looks kind of familiar. How many of you have seen this formula before? About half. This formula has a name. Does anybody remember the name? Yeah, this is the quadratic formula. So, what this says is the solutions to the equation ax squared plus bx plus c equal to 0 can be found by doing x squared, or x equals negative b plus or minus b squared minus 4ac all over 2 times a. Should you memorize the quadratic formula for this class? Yes. Yes. That is something you'll get tremendous mileage out of. It's well worth your time to do that. As long as we're on the topic, next time we have class, you should absolutely bring your graphing calculator. We're going to be using our graphing calculator in class the next time. You want to make sure you have your own graphing calculator because we're going to do a little bit of programming on our graphing calculator, and you'll definitely want that program on your graphing calculator going forward, the one that we're going to write in class together. So don't borrow someone else's because that's not going to help you when it comes time to use it again because you won't have someone else's calculator. Bring your own calculator next time because we're going to do some programming together and you'll definitely want this program moving forward. Okay? Okay, so some examples now. So let's say we have x squared minus 5x minus 13 equal to 0. At quick glance, can you factor this? No, why not? There's not two numbers that multiply to give me negative 13 that also add to give me negative 5, right? Should be easy to kind of see that immediately since 13 is prime. There's not a lot of options there that are going to multiply to give us negative 13. Okay, so what can I do? I'm going to use the quadratic formula. What is my values for a, b, and c that I'm going to be plugging into the quadratic formula? A is 1, B is -5, and C is -13. Everybody okay with that? All right. So I'm going to have negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Notice the way that I've typed in, or the way I've written down, -5 squared. You need to make sure, if you're typing this into your calculator, that you put your parentheses in that same locations that I've done in this problem. If you do not do that, you're going to end up getting the wrong answer because your calculator is not going to be doing what you mean for it to do. So, negative of -5 is +5. 5 squared is 25. -4 times 1 is -4. And -4 times 13 is +52. And that's all over 2. 25 plus 52 is 77. And the square root of 77 is not a perfect square. And I can't simplify the square root of 77 anymore because 77 doesn't contain any perfect square factors. Its prime factorization is just 7 times 11. So this is as good as I can do. Now, if I'd like decimal answers out of this, I could certainly do that. So the way that I can do that is if I take my calculator, I'm going to type in 5 plus the square root of 77 divided by 2. Notice I had to put a parenthesis around the entire numerator. So that's one answer. And my second answer I can get by pressing second and enter, and then just going back and editing the plus into a minus. So my second answer is -1.88, yada, yada, yada. So I am getting 2 answers there. I'm just writing it in a really compact form. Everybody okay with that? Okay. Notice, oops, we had talked about a way to check to see if things like this were factorable. Does anybody remember the formula that I gave you to check to tell if something was factorable or not? We looked at the square root of b squared minus 4ac. Notice what that is. It's just part of the quadratic formula, right? In fact, if a, b, and c are whole numbers, the only thing that's going to prevent the solution from being a whole number is if that square root doesn't work out to be a perfect square. So that's really the sticking point on whether something's going to be factorable or not, is that value there. We call this thing the discriminant, as an aside. And we'll talk more about that later. Check. Yeah, if you could simplify the radical there, yes, I would. Anytime you simplify the radical to simplest form, when you're not asked, or when possible to do that, I would count those as extra credit opportunities. So there could be lots of those inside of the test. Now, I'm not going to be so silly as to include like 50 points of extra credit on a single test, but there'll be opportunities to do that. And we'll talk, the reason I'm going to count these as extra credit is because we have a whole unit devoted to radical functions, and we'll talk really long and in depth about how to deal with like simplifying expressions involving square roots much later, because we haven't talked about that yet. I think it's an unfair expectation to expect that you're able to do that now, although it's not a difficult skill. If you're not comfortable doing it, it certainly just adds one more thing to an already increasingly long list of tasks for this chapter that I don't want to do. But if you're able to do that and you feel like you're going to put the time in to do it, I want to reward you in a way. Okay? Okay. Let's do another. Could I solve this by factoring? Heck, I don't know. Why is this going to be hard to tell if I can factor this or not? That leading coefficient isn't 1, right? So it's a little bit harder to tell right away at first glance whether this thing is going to be factorable or not. If it is factorable, I know I'm going to have to use that long factoring method on it anyways. In my opinion, that's not any easier than just using the quadratic formula. And I'm not even guaranteed to be able to factor it if I am able to, if I do try to factor this. So why would I even bother trying to factor this? I probably wouldn't. So unless you're directed specifically to factor something, if the leading coefficient isn't 1 and you can't make the leading coefficient 1 easily, I would just use the quadratic formula, which is what we're going to do right here. So I have negative 24, 12. That's A. Okay, I need my calculator. 24 squared is 576. Negative 4 times 12 is negative 48. Negative 48 times negative 25 is positive 1,200. And 2 times 12 is 24. Now, 576 plus 1,200 comes out to be 1,776. I'm not sure if that's a perfect square or not, so I'm just going to check it on my calculator real quick. I get a decimal when I take the square root of 1,776, so I know that's not a perfect square, but it might be able to reduce. So let's look at the prime factorization. So I know that 1,776 is even. So I know I can take a 2 out. And 888 is even, so I can take a 2 out. 444 is even, so I can take a 2 out. 222 is even, so I can take a 2 out. 111 is divisible by 3. You know how I can tell if something's divisible by 3 really easily? If you add up the digits, and the sum of the digits is divisible by 3, that number is also divisible by 3. So because 1 plus 1 plus 1 is 3, I know that it was divisible by 3. That's a neat little divide by 3 check. It only works for dividing by 3, but it's sometimes helpful. So if I look at this, I have a 4 and a 4. So this would be like the square root of 4. This would be like the square root of 4. This I can't do anything with, so I'm just going to make that the square root of 111 again. So when I simplify that, I have 2 times 2, which is 4, and then the square root of 111. Okay with that? And now, there's still a little bit more simplifying I can do. Notice that if I look at the coefficients here, Negative 24, positive 4, and positive 24. Do you notice something? They're all divisible by 4. So I can do that and simplify this down to 6 plus or minus the square root of 111 over 6. What do you guys think? So that wraps up our solution or solving techniques. So let's just kind of recap what we have here. So solving by factoring. What are our pros? It's potentially very fast if you're good at it. What's the biggest con? Doesn't work all the time, right? We have solving directly. What's the pro here? Again, it's fast. The con is, well, it's unless we have one kind of x, it's not fast. So what you guys know what I mean by one kind of x? Either an x squared or just, you can't have an x and an x squared at the same time, right? Okay. The last one we've talked about is the quadratic formula. What's the biggest pro here? Always works. The cons, it's like medium time consuming. Right? It's not quite as fast as factoring when the factoring is easy. Not quite as long as having to solve directly if it's not in the right, not in a convenient form. It's kind of like a medium time consumer. But it always works, which is nice. You don't have to deal with that, although you might have to do some rearranging before it's able to work. But that's the gist of it. So next time, we will be programming our graphing calculator to do the quadratic formula for us. So what we'll do is we'll write a program where we just input the values for A, B, and C, and the calculator will output the solutions, and we'll use the quadratic formula to do that. Everybody okay with that plan? Good. Stop this.